All right, let's start class. Okay, cool. So, come over, humans. No, that's fine. All right, so we pretty much finished up area between curves last time. There's like one thing we didn't get to on the worksheet about that I at least wanted to mention, and that was this like number 4, basically. Right, so like we have a couple of ways we can interpret this, and if you remember, I started with that like picture of, we have our economy here in the class prep video, and then it was, or like our economy here, and then like our economy with the coronavirus or something, where everything is worse. And basically you could look at like your area. Nice. You can look at your area between, and I mean, sure, you can talk about it as area, or sorry, F minus G, maybe I'll say. Right, this is the area between. But that doesn't really tell you much, right? Like if I say this area, like what am I really saying? If I ask like, oh, what is this telling me? And with regards to like the economy, I'm just like, oh, well, there's a lot more area in between. It's like, cool, man. I don't know what the area tells me about economy. So this is where, right, we also know from the fundamental theorem of calculus, right, that in general, this guy is like the net change in the antiderivative. Right, so if you're talking about like a rate of change of an economy, then this would be the result, right? So like the antiderivative, if the rate of change is the derivative, this would be the actual net change in the economy in, dollars or billions of dollars, whatever. So this is like net change in the antiderivative. And so another way to view this is it's the net change in the antiderivative of the difference, or difference of antiderivatives, right? You can either split up the integrals or put it in. So maybe I'll even say the other one because that's probably what makes more sense in terms of the real world. So net change in the difference between the antiderivatives. Right, and so if this is like time rate of change in, dollars per month, I guess, I don't know, then your antiderivative would just be straight up like dollars, like net change, like how much did we gain or lose over this period of time, and this would be like in the event that you have the virus, this would be if you didn't, and so if you wanted the difference between them, right, this would be like the difference between the net changes, or basically like how much better would the economy have been if this didn't occur. And so it can answer some really good real world questions when you interpret it that way. So it's important to think of it both as area, so you can actually like compute this as a region and figure out that like, yes, you should be talking about the integral, but also in terms of applying it to the real world to think of it as this difference between net changes. Okay. We have a sparse crowd today, according to my views. It's fine. So arc length is like a complete change in direction, it feels like, maybe. It does, basically we're looking at some applications of the integral, right? And these are like pretty geometric in general. So like one was area between curves. After we do arc length for a bit today, we'll talk about like computing volumes. That also has to do with integration. And so this is kind of applying the things that we learned at the very start of class. And yeah, as you guys kind of noticed last time, like hopefully this feels a little more chill after, the long slog. I mean, the series chapter is really long, right? 7 sections. We were in there for a while, and it's a difficult concept. So hopefully this feels like a bit of a reprieve. And goes well. So arc length, we won't spend a lot of time on. It's good to know, but as I mentioned in the class prep video, the formula that you get is often quite challenging. Like most of the integrals just aren't doable, and so like there aren't a lot of great examples. We'll have one today where we can really do it, and I did want to talk very briefly about the one on the class prep because I saw a lot of people trying methods that would fail or missing something very small. So if I want the arc length of the curve given by f on the interval from a to b, then this is equal to the integral from a to b of square root of, it's not f prime, it's f prime squared. So this is one thing, and this is also, I think, why some people had different answers. Plus 1, that 1 is under the square root, dx. Right, so the one you had to do on the class prep, right, was f of x is x squared. And so if you didn't square it underneath, you get 2x plus 1, in which case, yeah, you do a simple u sub, and that's easy, but it turns out that that's not what you do, right, because we need to square this. And so we can rewrite it as the square root of 4x squared plus 1 dx. And now if you try u sub, what goes wrong? Why is u sub bad here? Series is booty cheeks. I'm not even sure if that's bad or good. I feel like people would differ on that. Also, why are there 9 people on Discord and 6 people in the stream right now? Seems like a bad idea for a lot of reasons. Mostly a virus. There's not an x outside the radical. Exactly, yeah. So, I mean, you would want u, right, you might try u equals 4x squared plus 1 or something, but then your du would be 8x dx, and there is no x. So we can't really do this, right? So what method can we use? This should look somewhat familiar in here. Yeah, it's a trig substitution. This should look like the arctangent, right? So in general, we have a squared. Yeah, we don't even really need to do it, but yeah, it's a trig substitution. It looks like arctan, and so it would be several steps and not that useful. So I mostly just wanted to see, like, okay, did you see what the trig sub was? Not, can you do it out? It's kind of a long integral, and the one I'll give you today that's doable is like much quicker, but I mean still not easy, because yeah, in general these are really hard to make easy, just because of the form of these things. The square root of something squared plus 1 is just rarely nice. Okay. Alright, yeah, just wanted to remind us that trig sub existed. Okay, so I want to just kind of follow this along together, so we're just going to do like 2 problems here. The first one is not really going to be a nice function necessarily, so like we won't be able to integrate it, but we can do the approximation. I want to know like the process here. So in this case, right, f of x is sine of x on 0 to pi over 2. Use basically we're going to break up our interval, right, use the points at x equals 0, x equals pi over 6, x equals pi over 3, x equals pi over, yeah, that's it, x equals pi over 2, to approximate arc length. So what should our first step be when doing this? I guess you don't technically have to do this, but I think it helps. Also figure out, like, is this an over or under estimate? If you just saw this problem, like, what would be the first thing that comes to mind to do? Yeah, drawing a picture seems like a good idea. So let's draw it. If you notice, pi over 6, pi over 3, pi over 2, these are equidistant, so they're all pi over 6 from each other. So, I don't know, I'll do pi over 2 here, and then this is about thirds, pi over 6, pi over 3, and then, we've got sine up here at, it's going to go up to 1. Now sine starts at 0, 0. And so we need to figure out, like, what are our points, right? So sine of pi over 6, so that's our shorter opposite side, so this is 1/2. And sine of pi over 3 is root 3 over 2. And this is roughly, like 0.86 or something like that-ish. I'll definitely put like an approximately there. I don't know it off the top of my head, but it's much closer to 1 than it is to 0.5. And so if I draw my curve, I want this to go through like roughly 1/2. Cool. And then I make this look not as terrible. Sure. Works for me. So this is at 1/2. And then this guy is up here, at root 3 over 2. Okay, and then for the actual approximation, right, we want to draw lines between them. So this is a straight line, straight line, straight line. And so we see that this is definitely an underestimate, right? What property of the graph is making sure that this is an underestimate? So obviously you can just draw this, but like, what do you think in general? If I know my function f is blank, or its graph is blank, then it's going to be an underestimate. Yep, concave down. Good. So that's what you're looking for there. So if concave up, it would be an overestimate. Okay. So now we actually have to compute this thing, right? So maybe I'll give these names. So C1, C2, C3 for their lengths. And so our approximation, right, is roughly their sum. Roughly. So how would I compute these? Let's do C1, for instance, here. Like, how do I actually get C1? I mean, that's definitely a key part, but like, how do I, this is a length, right? So like, how do I calculate this length? Also, I know that a lot of you guys not named Reese have microphones. you can use those instead of typing, you know. Yeah, distance formula. Okay, so our distance formula here, right, is change in x. Well, in all of these cases, that's going to be pi over 6, right? So this is like pi over 6 minus 0 squared plus the change in y, which is 1/2 minus 0 squared. And you get some thing. I don't know what it is. I know what the sum is roughly, but yeah, this is something nasty because you have a pi over 6 squared in there and you're taking the square root. So then C2, right, so again, this would be like pi over 3 minus pi over 6 squared. That is pi over 6, by the way. And then plus root 3 over 2 minus 1/2 squared. And then lastly, you have pi over 2. Just kidding. 1 is on the next part. Pi over 2 minus pi over 3. Again, that's pi over 6 plus 1 minus root 3 over 2 squared. And then this ends up being like roughly 1.92, you know, as whatever that means to you. Yeah. Okay. Questions on that process? Right, and then yeah, you take the square root after that because you would get c squared, right? And you want c. So yeah, that's exactly how you get it. Right, because this is our change in x, this is like our a squared, and this is our b squared, so yeah. And I just want to note here that the actual arc length, I mean, we have a formula for it, right? This is, the derivative is cosine, so it's like cosine squared x plus 1. But this integral is like not doable without, I mean, you can do like numerical approximation for it, but this does not have any nice form in terms of elementary functions, so ugly. So that's why we often are doing the approximations. And so you might imagine, right, you can do sums of these, and like if you were in Mathematica or something, you could do a bunch of sums and calculate really nice approximations by, well, how would you approximate this more accurately? If you know the integral is really hard, but you want to approximate it, you know, better than what we just did, right? If my picture is an indication, we have like a decent amount of gap in here. How do we decrease the error? Yeah, just use more points, which gives us closer intervals, yeah. So if we took, 20 points in between 0 and pi over 2 and connected the lines, we would get a much more accurate approximation. So numerical approach with more points for accurate approximation. Good. Okay, so let's do one where we can actually do it. So you have to come up with some functions that look kind of weird. So we have the ln natural log of secant of x, and we'll go in the interval 0 to pi over 4. So let's go ahead and actually look at this. Where is my Desmos? I don't know what Desmos is. This is Desmos, yeah. Okay. So this is our, so if I zoom out, right, then this is what you actually get with the natural log of secant. It looks terrifying, but we're on 0 to pi over 4. Pi over 4 is small, right? It's less than 1. And so we'd really be looking, you know, something in here-ish in terms of our point. You can't see where I'm pointing, can you? But yeah, roughly around that like 0.8 line, 0.75-ish, right? So it's pretty small. I mean, we could even go smaller here. And so we're looking to trace it just along this little part, and so we don't have to worry about these asymptotes that happen if you go farther out. Okay, so how do we actually do this? Well, here we can actually use the formula. Okay, what is my derivative here, right? So my arc length is going to be the square root of dy dx squared plus 1, but like what is dy dx here? Yep. Okay, so right, we do our chain rule. So from the natural log, we have 1 over our inside times derivative of the inside. And that cancels out to just be tangent. Okay, so then my arc length is the square root of tangent squared plus 1. Oh, I'm sorry. This is the integral from 0 to pi over 4 of this. Okay. This still looks like a pain. Is there a way we can rewrite this that is useful? It's a leading question. There obviously is. So what is it? What is the nice way to rewrite this? Do we remember our trig identities for this guy? Yep. That's secant squared. Okay, and so square root of a square is pretty easy. So now we've got secant. And then this has kind of a nasty derivative, or antiderivative, but like it is doable. So this is the natural log of the absolute value of secant plus tangent. And so, okay. So secant of pi over 4 is root 2 over 2, or sorry, cosine of pi over 4 is root 2 over 2, or 1 over root 2. And so secant of pi over 4 is root 2. Tangent of pi over 4, well, that's when pi over 4 cosine and sine are the same, right? So the tangent is 1. And then at 0, well, cosine of 0 is 1, so secant of 0 is also 1. And then tangent of 0, well, sine of 0 is 0. So it's 0 over 1, which is 0. So our end result is just the natural log of root 2 plus 1, because the natural log of 1 is 0. Right? And then this guy is like approximately 0.88 or something like that. Okay. Questions on arc length before we change gears a little bit. The next section will definitely take us the rest of today and probably Friday. Yeah, we should do enough examples to fill Friday for sure. volumes. Okay, seeing nothing, we shall move on. So isn't this calculus 1, at least in my country? It depends. So it typically is calc 2 here, but you know, some calc 1s might get there. It depends on what you do at the end with integration. All right, so volume, so this is like 7.2 in our book, if you want to follow along. So the idea here is, again, so if we want to see how integration applies, right, then we want to be summing up things, because Riemann sums are how we get integration, right? It was the same thing with our arc length, right? How'd the integral show up? Well, we were adding up these lengths of our line segments, and then if you take more and more of them, right, you do a closer approximation, then you're summing up more and more, and then you take that off to infinity, right, and basically you've got yourself a Riemann sum, and then the limit gives you the integral. So that's how integrals come in there. How are integrals going to come up with volume? Well, let's just take something I can draw, some sort of loaf, I don't know, cylinder, potato-like object, we'll say, potato-like object here, right? So this is like three-dimensional, and so the idea behind this is, if I want to find its volume, then I want to be taking pieces that are easy. So let's first consider something easier than this, right? Because this kind of tapers off at the edges, and so it's not always the same width. So if I take a cylinder, I realize that I never draw cylinders laying on their side. All right. Whole cylinder and then 2 halves of a sphere. I don't know if these are spherical on the edge, but that's kind of the idea a little bit. Okay, so you've got a cylinder here. That looks ridiculous. Looks like a terrible drawing. Should this be the other way? Yeah. Yeah, so that is the idea, to split it up into a bunch of circles and then add it all up. And you can do that with the one up above too, it's just that your circles don't all have the same area. Right, so basically you want to think of a cylinder as like stacking a bunch of thin slices together. Right, that are all circles. That are all circles, right? You look at the cross section. So let's just say our thing here is h, because usually we stand it up and we already know our volume formula for a cylinder is pi r squared h. So let's just see that actually like works out here. And then we'll say that this has, you know, radius h here. Then what is our cross section? Well, if you take a slice, right, you just slice it right through and you see what that looks like, then it's a circle that probably doesn't look as terrible as that, and it's just this circle of radius r, right? You basically have taken away the height aspect, you've reduced it to a two-dimensional thing that you're dealing with rather than a three-dimensional thing. And then, well, we know that the area there is pi r squared, and then you're basically adding up a whole bunch of these things. So, I mean, technically this has no volume, right? It has no width whatsoever. So you don't technically want to do that. What you really want are these infinitesimally thin slices. So, infinitesimally thin, cylindrical slices that approach your circular cross section. And so what you're doing is the volume of your whole guy is split up into the volumes here. How about I will write it? So let's just split it. So let's say this is like x0, x1, pretend these are super thin. It's hard for me to draw things that are much thinner, right? So I basically split it into 1, 2, 3, 4 slices. And so this would be like the sum from I equals 1 to 4 of the area, of the volume of the little guys and basically what are these? So this is pi equals 1 to 4 of basically it's your area cross section at that point times like this delta x, like how much you have changed, right? This is, we know how to do little cylinders. And so this one, I mean, you know the whole cylinder, but now think about how this would work up here, right? You split this guy up. And so now, let's actually, I'll just redraw it down here. That makes way more sense. So if we have, x0, x1, x2, x3, x4, then the volume of this guy is equal to the sum of, again, the volumes of cylinders, but these are of different radius, right? Like the cylinder you get here, when you take that cross section, is going to be, is going to have a greater radius than the ones on the edge, essentially. And so like splitting it up allows us to deal, so like once you do just a simple cylinder where the radius is constant, now we know how to deal with things that are not constant. You just split it up and take small slices that are constant, right? Similar to like when you have a curve and you want to take the arc length, it's like I don't know how to do a curved line, but I know how to do straight lines, so I'll approximate my curved line with a straight line. So here it's like I know how to deal with like a prism where my radius is constant, so I can deal with a cylinder. I know how to do with like a rectangular prism or just like a box, right? Like I know how to do these volumes, and so now I can use those as like the building blocks of these weirder shapes. Does that make sense? So we're going to actually like show this more. And again, I want to make the point of rewriting it like this. So when I write AXI delta x, what I'm saying here, right, is my delta x is how wide this is for my cylinder, and then my A of xi is my cross-sectional area. So as long as your radius is linear, you can figure it out for each one. You don't necessarily need, you just need a formula that is integrable for your radius. It doesn't have to be linear necessarily. So, and in this case it wouldn't be linear, right? Because like look at your radius. I mean your radius is basically looking at these distances here. So like your radius function is exactly this like semi-ellipse, right? The top half of an ellipse. So this is very much not linear, but it is doable. Yeah. So how does integration come into play? Well, you can kind of see here, right? We've got our delta x, and if I want to get a better approximation, right? So most accurate approximation will take number of cross sections to infinity, and so basically you have this like limit as n goes to infinity of these things, right, of the areas of the cross sections times how wide they are, and then all you have to do is realize that this is exactly the integral on whatever interval you're talking about of a of x dx. So basically it boils down to find some formula for the area of your cross section given your x coordinate, or y coordinate if you do it vertically, and then just integrate that. So basically that should also make sense, right? Because when we integrated for, you know, just like a regular function in the plane, right? We went from something like one-dimensional, a curve, to the area under the curve. An area is like a two-dimensional thing, right? You now have all this area down below, so you've kind of like, you've gone from this guy to all this stuff below, so now you have like this two-dimensional thing. And then if you integrate area, you kind of jump it up one more dimension to volume, which is you're usually talking about like three-dimensional things, right? So it shouldn't be shocking that like the integral of area should somehow be volume, and like this is the way that you think of it that makes it work that way. Questions? Okay. Let's do an example then. All right. So we know this. So I guess maybe I can say one more thing here. So this is like theorem in the book that I can just kind of state directly, right? So volume for a function. Okay, so you have to draw it a certain way, basically, right? So like if I just draw a potato guy, I don't have a plane, but suddenly I drew axes on it, right? And now I can kind of make things work and consider a function and stuff like that. If it's just out there in space with no coordinates, I don't really have a nice way to turn it into functions, right? So that's kind of your first step. So if the base of a solid lies on the xy plane, I'm just going to write this kind of verbatim. Maybe I should have had this already written, but between vertical lines x equals a and x equals b, this kind of gives you your bounds for your integral, right? All right, we're back. Okay, and then for x in this interval, let a of x be the cross-sectional area perpendicular to the base. Perpendicular to the base. So we'll draw a picture here in a second. Then if your integral makes sense, so we'll just say area is continuous, which for us it's going to be, if A is continuous, then the volume of the solid is the integral from a to b of a of x dx. Okay, so this is just a lot of words, I guess. So let's think of how to actually draw something here, right? Okay, so the base of our solid lies on the xy plane between vertical lines x equals a and x equals b. Okay, so let's check that this works for the cylinder. What would actually be more interesting? Would that be? Nah, that's fine. This works for the cylinder. Or we could do the sphere. That would be kind of cool. Because the cylinder is kind of hard when you think of it that way. What do I want to do? I want to do the pyramid after, but that's probably too hard to start with. So let's see, check that this works for, let's just do Dr. Gates, check the Twitch chat. Yes, I am aware of the cylindrical shells method. Yeah. We'll be talking about like the disc washer. We won't probably be doing shell method in this class, but we'll talk about the disc and washers probably on Friday. That's probably a little too far today. So basically the idea there that we'll get to is that you can revolve things. So I'll just draw a picture real quick as kind of a teaser for what we'll do Friday, right? So like one way to view a cylinder is just take this guy, right? This would be your radius. And then how do you make a solid out of it? You revolve it around the y-axis, right? And then suddenly you have a cylinder because you've just like windmilled it around your y-axis and you've like filled out what that rotation would give you, right? We're making area throughout all of that, and so that'll fill out a whole cylinder. And so basically you can view that with having like all circular cross sections. So yeah, let's check that this works for like a rectangular box. So I'll just erase this. Or just, yeah. We'll just do a box, square box. Or a rectangular bit, yeah, I just want a square base because that's the easiest thing for me to draw. So how about a rectangular prism with square base? Okay, so that tells me that if I have square base, right, then I'm going to draw that guy in the plane. So I draw the base in the plane. And we'll just say our base is W, length of base, and H is our height. And this is a square base, right? So the length equals the width here, so I only need to talk about one. So if I want to draw the base in the plane, I mean, you can draw it basically wherever you want. You can start it at 0. You can go like somewhere else, but I think this is fine. Yeah, I'll just do it like that. I'll just do here in the first quadrant. So I said the length of the base is W, so this would go up W, W, and obviously this is 0. And so what I'm doing is I'm basically building on top of this, right? So like coming out of the screen would be the height of your rectangular prism. So you can't really like see that here, but you can see like where the cross sections would be, right? So like we're talking about cross sections perpendicular to the base. So if we're going in the x direction, we would draw this. This would be for the x direction. You could alternatively integrate with respect to y if you wanted to, and there you would just go up, right? So there you go in that if you wanted to integrate like area with respect to y, dy. And sometimes that will be easier. It just kind of depends on how you like to draw things. And here, obviously, it's going to be symmetric. So if we go in the x direction and we look at these cross sections, right, then what is our a of x, right? So this is the area of a cross section. So basically, you pick an x, and we want to see what does this cross section look like. So I know I'm going to slice down my whole rectangular prism, down to this bottom line on the square base, right? So what is that cross section going to look like? What shape is it? What are its dimensions? So what is our cross section? Thoughts? So they're not actually squares. So remember, when we go up, our height may not be the same as our width. So we might be going up higher than this W. So we know what the bottom of our cross section looks like, right? The bottom of the cross section, this is like in the base. This is definitely length W. Yeah, these are rectangles. So, right, like this is the thing that you're seeing here. That's this guy. This is what's in the base. It's length W, and then it goes up the whole height of the prism. And so this is H. Does that make sense? Thanks. Okay, and so our area here is what? Well, it's HW, right? And notice that it doesn't depend on x. I say it's a function of x, but it doesn't depend on x. Why? Because the area of all of these cross sections are equal, right? All the cross sections look exactly the same because it's a prism. So for like a pyramid, it's going to be different because you're going to be like coming to a point. And so these will have like different widths throughout. But these all have the same cross section. So this is our function. And so what we do is, well, remember, we had until W here. So on the x-axis, we go from 0 to W of this a of x function dx. And so we get hwx from 0 to W, and you get hw squared. And that's exactly what you would expect, right? Because it should be just length times width times height, and here length is equal to width. So it checks out with like what you would hope is true. Yeah, so let me just kind of get you started on a pyramid. So for me, and I may talk about it, well, I'm definitely going to talk about it in our class prep, but for me, it's often useful to think of, you know, do I want to do it with respect to y? Do I want to do it with respect to x? For me, a lot of the time, it's actually easier to, I don't know, I draw my pyramids like this. You know, I don't really draw them lying horizontally. So with the pyramid lying like this, you know, say it has height h, then what you're looking at are cross sections, say here, right, at some value y. And then it's going to be your cross sections here, right? So if you have a pyramid with a square base, right? So like this whole guy is, say, length r, or we'll just say length b, length of base. And this will be like a square base, because I realize you can do like a triangular pyramid as well. But yeah, then all of these cross sections, right, you have just like squares going up, but they're getting smaller and smaller until you reach that point. And so you have cross sections that are squares, But the difficulty here is these are of differing side length. Right, and so if you have different side lengths for these squares, you have to figure out what it's actually going to be at some point y on your y-axis. And there, if you see this, you have a triangle here, you have another triangle here. So you should use similar triangles to figure out the side length. So we're pretty much out of time, so I won't like go through that whole thing, but I'll probably do it in the class prep. But this is kind of the idea. So you just want to, put your base there and figure out, okay, what are the things I'm getting as I go down. So here I have like a square of side length b, but then by the end it's side length 0, right? So I've got a shortening side length throughout. And my goal is to find like what is this length right here in general. Any questions? What the heck? All right, well, I will go ahead and stream. We don't technically have office hours until 3 today. If algebra kids don't have questions, I can potentially answer some. So I'll be around in Discord.